All right, this is section 7.1, part 2. We're going to talk about how to use the substitution method. So solve one of the two equations for one of the variables in the term of the other. Substitute the expression for this variable into the second equation, then solve for the remaining variable. Substitute that solution into either the original equation to find the value of the first variable. If possible, write the solution as an ordered pair. Check the solution in both equations. So, can we use a substitution method for any linear system that we come into contact with? Yeah, the answer is yes, you can, but this method works best if one of the equations contains a coefficient of 1 or negative 1 so that we do not have to deal with fractions. So notice here, I'm going to use substitution, not only because they asked me to here, but because I have a coefficient of negative 1 here, or because I have a coefficient of positive 1 here. So I'm going to use, we'll say this is equation 1, equation 2. I'm going to solve for equation 1, either x or y, doesn't matter, I think I'll solve for y. And then I'm going to substitute it into the second equation. So I'm going to add x to both sides, so y is equal to x minus 5. Okay, and then what I'm going to do is I'm going to plug in everywhere I see a y, I'm going to plug in x minus 5. And now I'm going to solve for x. So it'll be 5x plus 25 equal 1. So that'll be negative 3x plus 25. Subtract the 25. So this will be x is equal to 25 over 3. Forgot to subtract on this one right here. So that would be a negative 24. So negative 24 over negative 3, that will give us 8. Okay, and then what I'm going to do is I'm going to plug 8 back into equation 1 or 2, doesn't matter which one, it'll come out to the same thing. So let's try equation 1. So I'm going to add 8 to both sides, so y is equal to 3. So the solution to this problem should be 8, 3. Now we can go back and check, which means plug it into both equations, and make sure that we get a true statement from both equations 1 and 2. Okay, so for equation 1, negative 8 plus 3 is equal to negative 5. Well, yes, that checks out. Okay, and then equation 2, 2 times 8 minus 5 times 3 is equal to 1. So this is 24. I'm sorry, that's 16. This will be 15. So 1 is equal to 1. Okay, so yes, this is the solution for this linear system. Now let's look at this one right here. So notice I have a coefficient of 1 right here, so I'm going to take equation 1, solve it for y, and then plug it into equation 2. So that means I'm just going to move the 12 over to the other side. So 19. So 12x plus 19. Okay, and then I'm going to plug this back into this equation here. So wherever I see a y, I'm going to replace it with 12x plus 19 is equal to 14. So negative 24x plus 24x plus 38 is equal to 14. Notice these cancel out, and I'm left with 38 is equal to 14, which notice here I have no variables, so all my x's went away, and I have a false statement. Okay, so when I have those two together, I have no variables and I have a false statement. In our last video, we talked about this right here. When you have no variables and a false statement, then what you have is parallel lines, which means they never intersect. And since they never intersect, that means that we have no solution. So for this problem, we have no solution. And there will be a another example here, but let me go ahead and show you in this example. Let's put both of these into y equals mx plus b format. So negative 12x plus y is equal to 19. We move the 12x over and got this right here. Negative 24 plus 2y is equal to 14. 2y is equal to 24x plus 19. Divide everything by 2, so y is equal to 12x plus 19 over 2. Now notice they have the exact same slope, but they have different y-intercepts. So when you have that, the same slope but different y-intercepts, and remember, it has, for the slope to be the same, it has to have the same number and the same sign in front of it. One can't be negative and the other be positive. That's not the same slope. So both of them are positive 12 for the slope. And one you have 19 for the y-intercept, and the other one you have 19. One you have 19 for the y-intercept, and the other one you have 19 over 2. So that means that you have parallel lines when that happens, which means you have no solution. So let's look at this one. Here I have a coefficient of 1, so I'm going to solve for equation 2 and plug it into equation 1. Okay, so this will be y is equal to negative 9x minus 3, so 27x plus 9 is equal to negative 3 times negative 9x minus 3. So that is going to be 27x plus 9. Okay, I'm going to subtract off the 27x, and I get 19 is equal to 9. Oh, sorry. 9 is equal to 9. Okay, so this is, we have no variables again. So all our x values are gone. And now we have a true statement. Okay, so when we have these two together, now we're talking about the same line. Okay, so we've got this right here. So when you got no variables in a true statement, we're talking about a same line, and they intersect at every point on that line. So we have infinitely many solutions here. Okay, so let's go back here. So we have infinitely many solutions. And let me show you, I'll show you this again later, but let me go ahead and show you now why that's the case. Okay, so we'll take the 27x plus 9 is equal to negative 3, and we'll go ahead and solve it for y. So divide everything by negative 3. So this will be negative 9x, 3, and y. Okay, so we'll put that in y equals mx plus b format. Okay, and then we'll do the same thing for this one over here. So I'm going to subtract that 9x over. So we get negative 9x minus 3. And notice how we have the exact same line. Both of them is y is equal to negative 9x minus 3. So when they come out to the exact same line, that means that you have infinitely many solutions. Okay, now let's talk about using the addition method to solve linear systems here. So what we're going to do is we're going to either pick the y or the x variables, and we're going to try to get them to the exact same number and then subtract the two equations from each other. Okay, and what we need to do is we need to get the x and the y variables on the left side of the equal side and the constants on the right side. Okay. So write one equation above the other, lining up corresponding variables. If one of the variables in the top equation has the opposite coefficient of the same variable in the bottom equation, add the equations together, eliminating one variable. So we're trying to eliminate either the x values or the y values. Depending on the question, I'll show you which one's easier to do. If not, use the multiplication by a non-zero number so that one of the variables in the top equation has the opposite coefficient of the same variable in the bottom equation. So you would want to get, say we're trying to get rid of the x values. Say we want one of them to be a positive 2 and the other one in the other equation to be a negative 2. And then when we add those, we're going to cancel them out. Okay, so let's look at, say, this one right here. So here's equation 1 and here's equation 2. Notice I don't have a coefficient of 1 anywhere. I have 7, negative 2, 3, and another negative 2. Okay. Now what I'm going to do is, for this one, I'm going to, number 1, I'm going to get the x values and the y values on the same side. So I need to move that 2 over. And then I need, so 3y, and that's a positive 3, move that 2 over, is equal to 16. Okay? So for this one, I can either get both of my x values to a 14 or both of my y values to a 6. So if I choose the y values, I would take this one and multiply it times 3, and take this one and multiply it times 2, and a negative 2, so that one of them is a positive 6 and the other one is a negative 6. Okay, so when I do that, we will have 21x plus 6y is equal to 15. And then negative 4x minus 6y is equal to a negative 32. And then we add these two together. So we get 21 minus 4, which would give us 17x plus 0y is equal to negative 32 plus 15, which is a negative 17. So I have 17x is equal to negative 17. Divide both sides by 17, so x is equal to negative 1. And then I can take negative 1 and plug it back into either equation 1 or 2. It doesn't matter which one. So say I plug it back into equation 1. Okay, so we would have negative 7 is equal to 5 minus 2y. I'm going to subtract 5 from both sides, so that's going to be negative 12 is equal to negative 2y. Divide both sides by negative 2. So y is equal to 6. So it looks like our solution should be negative 1, 6. But we always need to go back and check just to make sure we haven't made any type of error. Okay, so I'm going to plug it back into both equations. So first one. So we got 7 times negative 1 is equal to 5 minus 2 times 6. So that's negative 7 is equal to 5 minus 12. Negative 7 equals negative 7. That one checks out. But we also need to check out the other equation, because if one of them passes but the other one fails, it's not a solution. Both of them have to pass. Okay, so 3 times 6 is equal to 16 minus 2 times negative 1. So that's going to be 18 is equal to 16 plus 2. 18 is equal to 18. So that means that this is a solution to this linear equation or system. Okay, let's look at this one, and this one has fractions involved. So I'm going to change this by getting rid of the fractions. Okay, so I'm going to multiply this equation by 6 and this one by 4. I'm just getting the LCD. So we can knock out a 3 and the 3. I'm left with a 2x plus y is equal to 3 times 6 is 18. 4 over 2, that's just 2, so that's 2x minus y is equal to 4. And notice I already have a positive and a negative y, so I can go ahead and, so this will be 4x plus 0y is equal to 22. So 4x is equal to 22. Divide by 4. So this will be x is equal to, I'm going to take a 2 out of both of those, so 11 over 2. And then I'm going to plug that back into either equation. And you should plug it back into the original, just in case you made a mistake with the canceling out. So we'll plug it into